Nvidia is a frontier AI model builder, and we build it in a very special way. We build it completely in the open so that we can enable every company, every industry, every country.
Welcome to Corporate Files Lab, briefings on AI, business, and geopolitics. This is Case File, #004, the $5 trillion sovereign. Today's briefing, physical AI and the end of the analog world.
The mission today is precise. We are not here to discuss new gadgets or iterative technology launches. We are contextualizing the recent flurry of announcements, particularly those orbiting CES 2026, as a calculated strategic infrastructure offensive.
So we're looking at this as a campaign, not a product cycle.
Exactly. We are analyzing Nvidia's comprehensive move to secure global operating system dominance, not just over screens and tokens, but over the physical, moving world.
That immediately reframes the stakes. We've all been focused on the dazzling outputs of generative AI, the images, the text, the code, which lives mostly in our digital space.
Right, and that was, the first wave.
But the sources are clear. The next $90 billion market, the actual prize, is physical AI.
Exactly. Generative AI is confined to the screen dealing with language and pixels. Physical AI, it requires intelligence to move, reason, and act in accordance with the laws of physics.
So we're talking about robotics, self-driving cars.
The full spectrum of autonomy. Robotics, industrial control, self-driving vehicles, logistics. This is the integration of intelligence into physical systems. And it's a seismic shift that forces us to move from focusing on model size to focusing on, model capability.
And leading this infrastructural campaign is CEO Jensen Huang, a figure who has become perhaps the most recognizable public face of this transformation. Our sources suggest his presentation, that ubiquitous black leather jacket, is no accident.
It's the uniform of a new kind of global technocrat. This is not the standard corporate CEO, right? This is an individual and a corporation that has strategically positioned itself to control what analysts now identify as the 5 critical layers of modern computing.
And what are those 5 layers exactly?
The foundation's the silicon, of course, but layered above that are the networking fabrics that allow the compute to scale.
Okay.
Then the underlying infrastructure framework, the actual AI models that run the reasoning.
And finally, the applications.
And finally, the applications that deliver real-world value. Control all 5, and you control the architecture of reality itself.
Which brings us to the core thesis we need to explore today. How is this vertical integration being achieved, and what are the implications of centralizing that power?
Well, our analysis suggests that in this new world order, defined by silicon and synthetic data, the foundational principle holds true. Information is the only currency.
Let's start at the very bottom of that vertical stack, the hardware foundation. The context here is just the blistering pace of acceleration.
It's incredible.
Nvidia is aggressively sticking to an annual product release, Cadence Hopper, Blackwell, and now the Rubin Architecture. Most companies would struggle to maintain that speed every 3 years, let alone annually.
That aggressive cadence is perhaps the single greatest source of competitive pressure in the industry. It's forcing the entire global supply chain. We're talking SK Hynix for memory, TSMC for fabrication,
And the hyperscalers themselves.
and giants like Oracle and Google for deployment to accelerate their roadmaps or, frankly, accept instant irrelevance. The scaling laws of AI, the observation that model capability increases with more data and more computation, still dominate the field.
And Huang has been explicit about why this acceleration is necessary. He keeps saying the demand is skyrocketing.
It's a geometric problem, not an arithmetic one. Models are increasing in size and complexity by a factor of 10 every year.
A factor of 10? That's hard to even comprehend.
It is. And at that rate of consumption, incremental upgrades simply won't cut it. The industry is rapidly hitting 2 hard limits: the memory bottleneck and a power bottleneck.
What we're calling the energy wall.
Exactly. And this necessitates not just a faster chip, but a radical architectural overhaul.
And that overhaul is the Vera Rubin NVL72 platform, named after the pioneering astronomer. It sounds like they are moving beyond viewing the chip as the key unit of measurement.
They absolutely are. The shift in terminology is crucial here. Rubin is positioned not as a single GPU chip, but as an AI factory.
An AI factory.
They have literally redefined the core unit of compute. It's no longer the single GPU server, it's the entire data center rack. The NVL72 rack, which integrates 72 Rubin GPUs and 36 custom Vera CPUs, represents an extreme co-design.
When you say extreme co-design, you're referring to the coordination of those 6 distinct chip elements required to make the system work in lockstep. Before we dive into the specs, can you clarify what each of these components does in the overall machine?
Certainly. This is where the integration becomes visible. The foundational processing happens on the Rubin GPU and the Vera CPU. That's the engine.
Okay, the brains of the operation.
But the power comes from how they communicate and scale. The proprietary high-speed connection between the GPUs within the rack is managed by the NVLink 6 switch. It doubles the previous generation's speed for just incredibly rapid communication.
So that handles communication inside the rack, but AI often requires massive clustering across thousands of racks, doesn't it? That's the whole point.
It does, and that's where the scale-out architecture comes in. You have the ConnectX-9 Super NEC for distributing computation across those huge clusters.
And the DPU, that's a term we hear more and more.
Crucially, you have the Bluefield-4 DPU, the data processing unit. Think of a DPU as a specialized computer dedicated entirely to offloading and accelerating networking, security, and storage tasks that would otherwise bog down the main CPU.
So it's like a traffic controller, making sure the main highway is clear for AI work only.
It ensures the GPU is spending 100% of its time on AI computation. And finally, the Spectrum 6 Ethernet switch, featuring co-packaged optics, manages the power-efficient scale-out across the massive, sprawling superpods.
That level of orchestration sounds overwhelming, but the result is what the hyperscalers, the Amazons and Googles of the world are looking for: raw, scalable performance.
That's the only thing that matters to them.
So what are the metrics that define this generational leap, especially when we talk about running these enormous models?
The jump is just staggering. The Rubin GPU delivers 50 PFLOPS of NVFP4 inference performance. That's a 5 times increase over the Blackwell GB200. I have trouble even conceptualizing numbers this large. Can we put 3.6 exaflop PS, the capacity of a single NVL72 rack, into perspective?
It's difficult, but imagine this. 3.6 exaflop is more raw processing power than the combined peak performance of the top 500 supercomputers in the world circa 2012.
Wow.
It's the processing power equivalent of a significant military or scientific research nation dedicated to running AI. It's truly monumental.
And this power translates directly into efficiency, which is the critical competitive lever for the hyperscalers. Nvidia is claiming a 10 times reduction in the cost per token for a mixture of experts, or MOE inference workloads. For training, it's 3.5x higher performance.
Let's slow down on mixture of experts, MOE, because this architectural efficiency is critical to the entire business model. What is MOE, and why does Rubin make it 10 times cheaper to run?
Well, MOE is an architectural technique for creating massive models that are sparsely activated. So imagine you have a complex problem, and instead of one monolithic brain trying to solve everything,
You have a team.
you have a council of, say, 10 specialized experts. When a user asks a question, the model routes that query only to the 2 or 3 relevant experts. This makes the model feel incredibly large, billions or even trillions of parameters, but requires far less compute for any single query.
Which makes inference faster and cheaper.
Right, so it makes inference scalable. You only activate the parts you need.
But that sounds like it would create a communication nightmare inside the system.
Precisely. MOE models are ravenous for bandwidth. They require rapid, high-volume internode communication between those specialized experts. This is why the industry was hitting the memory wall.
And Rubin solves this how?
It specifically addresses this by integrating the latest HBM4 memory, delivering 22 terabytes per second of bandwidth per chip package.
22 terabytes per second.
It's nearly 3 times faster than previous targets, and is the necessary infrastructure to feed these distributed MOE architectures efficiently.
But memory bandwidth, even at that speed, only addresses the speed of the data transfer. It doesn't solve the core problem of context windows that are growing longer and longer models that need to remember millions of tokens. That memory footprint itself becomes the bottleneck for inference, doesn't it?
That takes us to the most ingenious piece of infrastructure co-design in this platform, the Inference Context Memory Storage, or ICMS.
Okay, what is that?
To understand this, we need to talk about the key value, or KV, cache. Think of the KV cache as the model's short-term working memory. As the model generates each new token, it refers back to the cache of the preceding tokens in the sequence.
So it's memory of the conversation so far.
Exactly. When context windows stretch to millions of tokens, say analyzing an entire book or a year's worth of corporate emails, that KV cache balloons in size and becomes the performance bottleneck.
It's like a person trying to keep every single fact from a 1,000-page report active in their short-term memory simultaneously. It's just unsustainable.
utterly. The ICMS, enabled by those BlueField-4 DPUs we mentioned, solves this. It creates a new high-speed memory tier explicitly designed to offload, share, and reuse that massive KV cache data efficiently across multiple GPUs.
So instead of every GPU keeping its own massive copy of the conversation history,
They share a centralized, instantly accessible library.
it's the difference between every bartender having to memorize every recipe every night versus having one instantly accessible networked knowledge base for the whole bar.
That's a great analogy. That allows for predictable, power-efficient scaling for complex reasoning.
And that complex reasoning brings us to the final component of this integration. The Vera CPU. It's not just a standard processor. It's customized for agentic AI, which is the workload of the future.
Right. We've used the term agentic AI a few times. Let's really define it in this context. Agentic AI involves complex, multi-step reasoning. It's not just answering a question, it's deciding how to answer it, breaking the problem down, checking internal facts, and executing a series of subtasks. It requires long thinking.
So it's more strategic.
Exactly. And the Vera CPU uses 88 custom ARM-based Olympus cores, engineered specifically to handle this complex orchestration and multi-step reasoning workflow.
And to support that long thinking, it needs massive memory capacity, not just speed.
Precisely. The Vera CPU features 1.5 terabytes of LPDDR5X memory, which is 3 times the capacity available in the Blackwell systems.
1.5 terabytes of memory.
That capacity is what supports the extremely long contexts, the millions of tokens demanded by agentic systems. This validates Huang's strategic insight. The future isn't just about faster calculations, but about having the space for deep, complex thought.
And finally, the price of all this power. The energy wall. The solution is no longer a matter of choice, but a requirement.
Liquid cooling is now the thermal management floor. It's a hard requirement for the highly dense NVL72 rack and even the smaller 8-way HGX systems.
And that has to be a direct response to regulatory pressure.
Absolutely. As the industry faces growing regulatory and environmental scrutiny, the focus shifts to efficiency per token. The fact that the next generation Kyber racks are projected to hit 600 kilowatts validates that energy consumption is the new strategic constraint.
So Nvidia is building a platform that manages this consumption, essentially internalizing a geopolitical problem energy into their hardware solution.
They have to. There's no other way to scale.
So we've established the massive power being built inside the data centers with Rubin, but that power is useless unless it can touch the real world.
Of course.
Now we follow the silicon from the rack out onto the asphalt. The next critical front in this campaign for the physical OS is autonomous driving, defined by Nvidia as the shift into AV3, agentic physical AI.
This is a fundamental philosophical shift in how we build self-driving systems. Generations 1 and 2 of AV focused primarily on perception identifying traffic signs, cars, pedestrians.
Just seeing the world.
Just seeing. But perception alone cannot solve the long tail problem.
The long tail being those infinite, rare, and unpredictable edge cases, the deer jumping out, the person jaywalking with a suitcase, the unusual construction detour.
Correct. AV3 demands the car operates like a capable reasoning assistant, not just a highly sensitive camera system. The car must reason about intent, plan multi-step maneuvers, and negotiate ambiguous situations.
So perception tells you what is happening.
And reasoning tells you why it's happening and what you should do next.
To solve the complexity of the long tail, Nvidia unveiled the Alpamayo family of models, simulation tools, and datasets. What makes Alpamayo the tool for this reasoning-based transition?
Alpamayo 1 is a 10 billion parameter vision language action, or VLA model. VLA is the fusion of visual input, natural language understanding, and physical action output. Its core innovation is what they call chain of thought reasoning. This is crucial because it takes the system from a reactive automaton to a proactive thinker.
Okay, describe how that chain of thought works in practice.
When a human driver approaches a complex intersection, we don't just react, we internalize a logic. That car is signaling right, the pedestrian looks distracted, I should slow down and maintain space.
We're running a constant simulation.
Alpamayo does this digitally. It not only generates the trajectory, the steering, braking, and accelerator commands, but it also outputs a parallel reasoning trace.
So it generates the decision and the explanation for the decision simultaneously.
Precisely. For example, the reasoning trace might read, I detected a cyclist traveling at 15 mph in the bike lane. My plan is to maintain current velocity and give 3 feet of clearance as required by local traffic laws, prioritizing the safe passage of the vulnerable road user.
That transparency is not just a neat feature, is it? You said it's a regulatory necessity.
It's everything. Why does a reasoning trace matter so much to regulators?
Liability.
When you move to level 3 and level 4 autonomy, liability is a huge concern. Regulators, particularly in the US and Europe, are deeply wary of black box AI systems that make safety-critical decisions without any verifiable rationale.
If there's an accident, they need to know why.
If an accident occurs, auditors need to know why the AI acted. The reasoning trace provides a mechanism for safety validation, auditing, and critically, acceptance by governmental agencies. Alpamayo is designed to perceive, reason, and act with human-like judgment, and crucially, explain that judgment.
And this technology is moving out of the lab and directly into mass-produced vehicles via the critical Mercedes-Benz CLA partnership. This partnership is being framed by analysts not as a simple car deal.
No, it's a genuine infrastructure conquest.
Right.
It is the moment Alpamayo moves from a demonstration to a foundational infrastructure component. The 2026 Mercedes-Benz CLA will be the first production vehicle to ship with the complete Alpamayo reasoning stack.
And the timeline is aggressive.
Very. U.S. launch in the first quarter of 2026, Europe in Q2, and Asia following later in the year.
And the hardware supporting this must be immense, given the complexity of the VLA model.
It is. The vehicle will deploy the MB Drive Assist Pro, which is an enhanced Level 2+ system running on Nvidia's specialized automotive hardware. That's Drive Thor, their new system on a chip.
And the sensor suite.
A comprehensive 30-sensor stack, 10 cameras, 5 radar, and 12 ultrasonics, all feeding data into the Alpamayo VLA model for real-time, reasoning-based decision-making.
This strategy places Nvidia in direct competitive conflict with internal efforts like Tesla's FSD, which maintains a fiercely closed, vertically integrated ecosystem.
Completely different playbooks.
Nvidia appears to be using a different playbook entirely, the Android of autonomy strategy.
This is the corporate Trojan horse. Nvidia is intentionally open-sourcing the Alpamayo 1 model weights, Alpasim, their simulation framework, and 1,700 hours of curated high-complexity driving data.
They're giving it away.
They are giving away the best ingredients for free via platforms like Hugging Face.
Wait, open sourcing massive, powerful, and proprietary models sounds inherently risky. Doesn't that just invite competition to build better software that runs on non-Nvidia chips?
It sounds risky, but it's a calculated, high-leverage move. Think about it. The immense complexity and capital required to build a competitive autonomous stack from scratch is prohibitive for virtually every traditional automaker.
They can't keep up.
Building the necessary data curation pipelines, the complex simulator, and the sophisticated VLA models is a decade-long, multi-billion-dollar effort.
So by offering the best open source foundational tools, the Android software layer, they commoditize the level 2+ market and make adoption irresistible.
Precisely. They become the indispensable utility. Automakers adopt Alpamayo because it's the path of least resistance and greatest speed to market. But here is the lock-in.
Ah, there's the catch.
To run that advanced performance-optimized high-parameter software stack efficiently, partners are implicitly and inextricably locked into the Nvidia hardware, the Drive, Hyperion Thor compute platforms.
You can have the recipe for free, but you must buy their specialized oven.
That's it, exactly. The ultimate goal isn't just selling chips to Mercedes-Benz. It's establishing the definitive global operating standard for the next decade of mobility infrastructure. They are building the AI railways.
They are seizing control of the AI railways.
And this mass adoption is already being explored by partners like Jaguar Land Rover, Lucid, and even research entities focused on Level 4 deployment roadmaps. By providing the common language for autonomous reasoning, Nvidia solidifies its architecture as the indispensable foundation.
Turning competition into coordination.
All focused on purchasing their high-margin silicon.
This reliance on reasoning and complex, multi-step actions leads us to the core challenge of physical AI. As Jensen Huang declared, the era when AI only communicated through screens and speakers inside computers is over.
A very clear statement of intent.
But the real world is chaotic, dangerous, and expensive for training.
That is the strategic choke point, and it's the vulnerability that Nvidia has targeted for its ultimate infrastructural lock-in. For physical AI to function, whether it's a self-driving car or a factory robot, it must learn common sense.
Physics.
Object permanence, causality, gravity, friction, inertia. You cannot learn these foundational rules in the analog world without immense cost, risk, and time.
Training an autonomous car requires millions of miles of testing. Training a complex warehouse robot requires hundreds of thousands of hours of hardware runtime. The marginal cost of training in the physical world is, well, it's near infinity.
Which is why the digital world must become the primary training environment. The solution is creating a perfect, physically accurate digital replica, the digital twin.
The metaverse for machines.
And this is where the thesis, information is the only currency, finds its most potent expression. If information is currency, then synthetic data generated in a controlled environment is the ultimate fiat money for AI training.
And the platform for generating that fiat currency is Cosmos, the World Foundation model ecosystem. How exactly do these World Foundation models solve the critical data scarcity problem in robotics and AV?
Cosmos provides open-world foundation models that understand the laws of space, time, and physics. Think of these WFMs as the AI's imagination engine.
Its imagination engine.
They are multimodal models, pre-trained on staggering amounts of real-world physical data, over 20 million hours of driving and robotics interactions, to replicate physical worlds as videos. They allow an agent to learn hundreds of millions of steps safely and efficiently.
Okay, let's break down the functions of the three core models within the Cosmos ecosystem as they define this synthetic data supply chain, starting with Cosmos Predict 2.5.
Cosmos Predict 2.5 is the generative engine. Given a multimodal prompt, a car is approaching an intersection at 30 miles per hour on a rainy day, it can generate up to 30 seconds of high-fidelity, physically consistent video of the future state.
So it's a prediction machine.
It allows the robot or AV agent to internalize future possibilities, which is crucial for sophisticated planning.
So it's allowing the agent to run a miniature simulation in its own mind. If I execute this action, what is the consequence 10 seconds from now?
Precisely. It turns the AI from a purely reactive entity into a strategic planner. Next, we have Cosmos Transfer 2.5.
And its function.
This is the data diversity amplifier. When developers have structured 3D inputs from high-fidelity simulators, Transfer 2.5 converts them into photorealistic video. This means developers can manipulate training conditions at scale.
So instead of having to physically wait for a snowstorm in December to gather training data, I can load a summer driving scene and instruct Transfer 2.5 to render it photorealistically under heavy blizzard conditions.
And you've instantly created a huge, diverse data set you couldn't get otherwise.
That's a massive advantage.
It's essential for robustness. Finally, you have the critical quality control mechanism, Cosmos Reason 2.
This one sounds like the philosopher of the group.
It is the curator. Cosmos Reason 2 is a reasoning VLM, spatio-temporally aware, designed to critique the synthetic data generated by predict and transfer.
It checks the work.
It uses chain-of-thought reasoning, the same kind of logic we saw in Alpamayo, to evaluate physical feasibility. For example, it ensures that in the simulated world, a generated video doesn't show a person walking through a wall or a ball rolling uphill without external force.
It screens out the physically impossible data, ensuring the AI learns reality, not fantasy.
It's the physics cop. This integrated loop predicting, transferring, and reasoning is how they create high-quality, physically accurate data sets at zero marginal cost.
And the physical environment where all this learning happens is the Omniverse platform, the high-fidelity 3D simulation environment, the ultimate digital twin.
And this is what we're calling the simulation trap.
Let's focus on that term, the simulation trap. What is the fundamental strategic implication here?
The integrated loop is now seamless. Omniverse provides the simulation environment, Cosmos models reason over that simulated data, and the resulting physical agents are deployed using Nvidia's edge hardware.
So the loop is closed.
If Nvidia controls the simulation environment, where the AI learns the fundamental laws of physics, the gravity, the friction, the causality, they are effectively controlling the AI's reality.
It's a profound statement.
Any agent trained in this environment will inherently adopt the foundational assumptions embedded in the Omniverse architecture.
It's setting the foundational operating system for physical intelligence. The agents practice hundreds of millions of steps safely in this virtual world before ever engaging physical hardware.
It completely de-risks and accelerates the development process. Jensen Huang's anecdote that robots from partners like Boston Dynamics are not walking on a real stage for the first time.
Right, they've done it millions of times before.
But have practiced millions of steps virtually confirms this. Simulation is the prerequisite to physical deployment. If you want a state-of-the-art physical agent, you must train it in the most accurate physics engine, and that is Omniverse.
And this applies directly to the specialized robotics framework, ISAC GR00T, which deploys this simulated knowledge.
ISAC GR00T N1.6 is the VLA model tailored for humanoid and industrial robots. It's the application layer, built directly atop Cosmos Reason, allowing for full-body control, fine motor skills, and contextual understanding.
And major players are already on board.
Global industrial partners, Boston Dynamics, Caterpillar, LG Electronics, Nearray Robotics are adopting this stack. This validates the physical OS across diverse sectors, from mining equipment to consumer service robots.
And the hardware supporting this, specifically at the industrial edge, has to be highly efficient to be viable in real-world energy-constrained environments.
The Blackwell-based Jetson T4000 module solves that. It brings 4 times the performance and 1200 FP4 TFLOPS to the industrial edge, running massive reasoning models.
And the power drop.
Crucially, it does this within an energy-constrained 70-watt envelope at a volume price of $19.99.
That's the key, that price point.
This democratization of sophisticated, energy-efficient autonomy at the edge is key to locking in the machine builders and ensuring the physical OS dominates every smart factory and autonomous machine.
This overwhelming push for vertical integration from the data center with Rubin to the simulation world of Omniverse was not born in a vacuum, though. It was shaped by a profound competitive shock that forced a massive strategic pivot.
The DeepSeek crisis of early 2025.
Exactly.
The DeepSeek shock was it was an existential threat to Nvidia's valuation and its core business model. In January 2025, China's DeepSeek AI released a model that achieved performance metrics that rivaled the best Western frontier models.
But that wasn't the shocking part.
No. The revelation was that it required only a fraction of the training investment and, critically, less reliance on the most expensive top-tier GPUs.
The market reacted instantly. Nvidia's valuation tumbled by hundreds of billions. The fear among investors was profound. If software optimization could achieve frontier model performance with less expensive hardware,
Then the whole game changes.
the fundamental scaling law that guaranteed continuous skyrocketing demand for the most advanced chips might be broken.
The market jitters were completely understandable. DeepSeek demonstrated that the center of value could potentially migrate from raw silicon horsepower to the software optimization layer. It raised the terrifying prospect that customers might begin substituting cheaper hardware combined with smarter code for the high-margin leading-edge chips.
It was a direct threat to the business model.
This forced a dramatic reevaluation of the entire AI economic structure.
Jensen Huang's counter-narrative had to be swift, aggressive, and deeply strategic to restore confidence. He reframed DeepSeek not as a threat, but as a catalyst for increased demand.
A very clever pivot.
But a demand for a different kind of compute.
His argument was brilliant. Huang asserted that reasoning models like the DeepSeek R1, which employ long thinking to make the answer smarter, actually require 100 times more computing power for inference than previous simpler generative models.
100 times more.
The success of DeepSeek, he argued, validated a new scaling law. The smarter the model, the more inference compute it needs, even if training was optimized.
So the threat was neutralized by redesigning the architecture to solve the very problem DeepSeek highlighted.
It's a direct architectural response, confirming that the new era is inference dominant. The heavy investment in the Vera CPU's custom cores, the massive LPDDR5X memory capacity, and the development of the inference context memory storage.
The ICMS.
All of it is designed to handle the long-sequence, computationally heavy inference demands of these sophisticated reasoning models. The design of Rubin validates Huang's claim. Long thinking makes the answer smarter, and Nvidia is the only entity built to provide that thinking at scale.
And analysts have since confirmed that the market jitters have not materialized because while optimization helps,
It only gets you so far.
running a truly massive frontier model still requires the advanced compute that only the Rubin architecture provides, validating billions in sales of Blackwell and now pre-orders for Rubin.
This leads us to the final strategic pivot. The recognition that raw chip horsepower is no longer sufficient for absolute dominance. The critical value resides in that software optimization layer, the CUDA software ecosystem.
And that necessity drove the seemingly contradictory move towards open source.
Right, we've seen them open source, Alpamayo, Cosmos, and Isaac GR00T. Explain again the logic behind giving away these powerful proprietary models.
It seems so counterintuitive.
It is the ultimate vendor lock-in maneuver, ensuring the CE gap remains unassailable.
The C gap.
By providing the very best open foundation models, making them easily accessible via platforms like Hugging Face Nvidia, democratizes access to intelligence for every startup, enterprise, and nation. Huang can honestly say, Digital intelligence cannot exclude anyone.
It's a good soundbite.
But the fine print is that the only efficient way to run those sophisticated performance-optimized open models is on their proprietary, highly integrated CU hardware stack.
So it all comes back to the hardware.
Exactly. The CU gap is the metric that quantifies how much more performance NVIDIA's integrated software stack unlocks compared to what raw generic hardware specifications might suggest. By controlling the optimal software layer for their open models, they ensure a deep vendor lock-in.
They are giving away the powerful software to guarantee the purchase of the specialized, high-margin hardware required to run it efficiently.
This strategy is about control, not philanthropy.
This synthesizes the entire deep dive then. Nvidia has successfully transitioned from being a chip vendor to a physical operating system provider. This is the structural reason underpinning the $5 trillion valuation.
The creation of the physical OS is complete and vertically integrated. It spans the entire stack, from the foundational silicon, Rubin to the simulation layer, Omniverse, the models, Alpamayo Cosmos GR0T, and finally, orchestration and deployment at the edge, always from Jensen,
It's an unassailable walled garden.
where the hardware is the software. This centralization of power, controlling the foundational compute for physical reality, is precisely what will face future regulatory scrutiny as it establishes a new global standard for infrastructure.
The narrative of this transformation is overwhelming. Anchored by the Rubin platform and the comprehensive physical AI strategy, we are observing a profound macro power shift.
It's undeniable.
The company has moved beyond mere hardware manufacturing to become the silicon sovereign, controlling the foundational compute layer for physical reality across the entire globe.
The vertical integration is total. They control the learning environment via simulation, the reasoning models, the network fabric, and the underlying silicon. This level of control over the infrastructure of the future is unprecedented in the modern technology landscape.
They are the standard setter for physical intelligence.
Effectively, yes.
So if the Rubin architecture proves successful and maintains this blistering one-year cadence, what does this aggressive, immediate future imply? If silicon design is no longer the critical bottleneck for AI expansion, where does the new choke point emerge?
The final provocative thought bids directly on the technical data we've discussed. The limiting factor for future AI expansion is no longer silicon, but global energy and infrastructure capacity.
The energy wall again.
The rapid pace of advancement, new flagship models every 6 months, and the sheer power requirements, with the 2027 Kyber racks projected to pull 600 kilowatts per rack, suggests the market must immediately pivot its focus.
It's a staggering number.
The next great investment frenzy won't be in the chips themselves, but in the power utilities, cooling specialists, and dedicated, robust energy infrastructure needed to keep these AI factories running 2047. They are now an energy company that also makes chips.
Case file closed. The future is being simulated before it's lived. New intelligence available every Saturday. You've been listening to Corporate Files. Subscribe to the channel for more briefings like this one.